In this video, we will be going over negative and zero exponents, and unfortunately, this lesson really doesn't fit in with this unit. So the big idea of this unit is to talk about quadratic relations, and negative and zero exponents, it doesn't really speak to that. But this concept of negative and zero exponents is in this chapter of the textbook, so I'm just going to follow along with that instead of moving it somewhere else. Okay, so when I think of negative and zero exponents, I think about what we did in grade 9. Okay, so hopefully your teacher in grade 9, or even in elementary school, did something like this. Okay, 4 to the power of 8 divided by 4 to the power of 5. And you will say 4 to the power of 3. So first of all, you should say, I'm dividing two powers with the same base, so I'm allowed to subtract the exponents. 8 minus 5 is 3. And you should also understand why you are subtracting exponents. And the rationale is you have 8 factors of 4 in the numerator, because that's what 4 to the power of 8 is. 1, 2, 3, 4. Did I write an extra one? No. There are 8 factors of 4, and there are 5 factors of 4 in the denominator. So you have common factors of 4 between the numerator and denominator. How many are common? 5, right? So you lose 5 from the numerator. You lose 5 factors of 4 in the numerator, because you have 5 common factors of 4 between the numerator and denominator. So you have 3 left. So it makes sense to subtract. Now, what I want to add here is the fact that in grade 9, you never did any examples where there were more factors in the denominator, meaning the exponent in the numerator is always greater than that of the denominator. Well, what if it was the other way around? What if it was 4 to the power of 5 divided by 4 to the power of 8? Hopefully, you will see that it's the other way around. There are going to be 3 factors of 4 left over in the denominator when you cancel out the common factors of 4. But what did we learn last year? You said that when you divide powers of the same base, you subtract the exponents. What's 5 minus 8? 5 minus 8 is negative 3. So that is actually what we want to summarize here. Okay, that's how we get a negative exponent. When you have more factors in the denominator, that's how you get a negative exponent. You have excess number of factors in the denominator. Whereas last year, you only had examples where there were excess number of factors in the numerator. Now, there's a third scenario. So the third scenario is when there's a perfect balance of factors compared to the numerator and denominator. So that's when you get a zero exponent. X to the b over x to the b, so that would be x to the power of b minus b. So there's a perfect balance of number of factors between the numerator and denominator, and you get x to the power of 0. So what is x to the power of 0? You know what? Let's, instead of doing x, let's replace it with some numbers. So you know what? We had a power of 4 here, 4 to the power of 5, 4 to the power of 5. So we know that's going to be 4 to the power of 0, right? Because 5 minus 5 is 0. But what you should really understand is when there's a perfect balance between the number of factors in the numerator and denominator, everything cancels out, right? So you're just left with 1, right? You can write down 4 to the power of 5, 4 times 4 times 4 times 4 times 4 in the numerator and in the denominator, but you know what? Let's write it out. Let's write it out. You'll realize that they all cancel out. Right? So they're all canceled. So really there are 3 scenarios. In grade 9, you only studied one of those scenarios. You can have an excess number of factors in the numerator. You can have an excess number of factors in the denominator. Or you can have a perfect balance of factors between the numerator and denominator. So that's what a zero exponent really means. So if we have the same number of factors after we cross out the common factors, we should be left with 1 when you cancel everything out. That's why x to the power of 0 is equal to 1. Now, small little note, we can't let x equal 0 because then you'll have 0 in the denominator, and we don't want to divide by 0. Okay, so x to the power of 0 equals 1 as long as we don't let x equal 0. Okay, in fact, when we do all these questions, like for example, if you look at these examples, we always assume the variable to be a positive number. In the homework, you'll see that we have a statement that we always let the variable be positive values. Anyways, back to negative exponents. So x to the power of m divided by x to the power of n is equal to x to the power of m minus n. So like I said, we only did examples where there are factors in the numerator. But if there are more factors in the denominator, that's when you get a negative exponent. So whenever you see a negative exponent, that quite simply means you have an excess of n factors. Because if the exponent's negative n, you have an excess of n number of factors in the denominator. So that's what a negative exponent means. Please don't think a negative exponent means the value is negative. In fact, if the base is positive and the exponent is negative, then the result is always positive actually. Okay, so let's simplify. And one thing we have to note is that when we simplify, we all agree that the final answer can only have positive exponents. That's considered simplified. Okay, but we'll add this statement anyways, just in case you forget. Okay, so our final answers can only have positive exponents. So if there is a negative exponent, like what we have here, y to the power of negative 3, we are going to write it as 1 over y cubed. So when I see y to negative 3, I quite simply think, there's an excess of 3 factors of y in the denominator. Okay, x squared times y negative 4. So be careful. Please don't move everything to the denominator. The exponent of negative 4 is only acting on y. So it's going to be x squared over y to the 4. Whereas this exponent of negative 2 is acting on ab. It's going to be 1 over ab all squared, which is 1 over a squared b squared, right? When you square all of ab, that means you square a as well as b. So that's basically from the exponent laws you learned in grade 9. Ooh, now you have a negative exponent in the denominator. So you know what? I'll break it down. I'll show all my steps. So it's 1 over a to the 4. And whenever you have, whenever you divide by a fraction, you multiply by a reciprocal. So really it's going to be 1 times a to the power of 4 over 1, which is a to the power of 4. So in essence, whenever you have a negative exponent in the denominator, it actually becomes a positive exponent in the numerator. So you know what? If the fraction business is really bothering you, because you really have a fraction in the denominator of a fraction, so what you can also do is change 1 to a to the power of 0, right? Because a to the power of 0 equals 1. And guess what? 0 minus negative 4, right? 2 powers, same base. Whenever you divide 2 powers of the same base, you subtract exponents. So 0 minus negative 4 is 4, right? So if that was bothering you, because a lot of students hate fractions, so if that was really bothering you, that's another way of seeing it. Okay. So here, a to the power of 0 is 1, so ignore that. When you cancel out the common factor, there will be 2 factors of b left over in the denominator, and negative exponent in the denominator, which means I'm going to actually have x to the power of 4 in the numerator. Okay. Over here, just follow BEDMAS really. Exponents first. So everything is going to be raised to the power of negative 3. So it's y to the power of negative 3. Power to power. So power of power means you multiply the exponents. Negative 4 times negative 3 is 12. And this is going to be y to the power of 9, z to the power of negative 6. Oops, that's a z. Okay, so now when you divide two powers of the same base, you subtract the exponents. So this is going to be x to the power of 8, y to the power of negative 12, because negative 3 minus 9 is negative 12. 12 minus negative 6 is 18. I'm running out of room, so I'm just going to slide that over here. So here, there's only one negative exponent. So the y, there's 12 factors of y in the denominator, but x and z are still part of the numerator. Okay. Before I do g, I'm just going to quickly prove this. So whenever you have a negative exponent, you can actually change the exponent to positive by quite simply taking the reciprocal of the base. So it's a very nice relationship. It comes very handy when you try to simplify these expressions. So I'm going to try to prove to you why that's the case. So I'm going to prove using, let's say, the left side. Okay, so we have a over b to the power of negative. I'm going to work with the left side. So what does that mean? You're going to have a to the power of negative n over b to the power of negative. That's what you did in grade 9, right? We have your base is a quotient, so you apply the exponent to the numerator and the denominator. Okay. Now we learned that, hey, if it's a negative exponent, if it's in the numerator, it goes to the denominator. If it's in the numerator, it goes to the denominator. If it's a denominator, it goes to the numerator. So you can actually write it as. And since b is raised to the power of n and a is raised to the power of n, we can conclude that b over a, all of b over a raised to the power of n. And we've proven that this, what we stated earlier, is correct. So this is a true statement. Therefore, there's different ways, there's different mathematical notation, but I'll introduce it when we get to grade 11. Okay, all right. You know what? Even do this. Left side equals right side. Okay, so we've proven that if the exponent is negative, you can actually change the exponent to be positive as long as we take the reciprocal of the base. So I'm going to make use of that, change this x over y to y over x, but now the exponent goes from negative 3 to positive 3. Y over x, the bases are the same, so I'm allowed to just add the exponents. Oops, oh my gosh, 2 plus 3, of course it's 5. And then y to the 5 over x to the 5. And that's it. So I know this lesson really doesn't fall into what we're trying to get across in terms of the big idea, but it's actually really nice because it ties together with what you did last year. You only looked at one scenario last year, okay, when there are more factors in the numerator compared to the denominator. But of course, you can have more in the denominator, or you can even have a perfect balance between the numerator and denominator. So really try to relate it to the logic of counting factors. It's really helpful.